What if the universe in all its majestic and intricate design had a family tree with a missing branch? Imagine a grand evolutionary story written across the cosmos detailing the birth, life and death of its most extreme creations. A story of titans where we can clearly see the infants and we stand in awe of the colossal adults. But when we look for the teenagers, the adolescents, the crucial link that connects one to the other, we find only a profound and unsettling silence. This is not a biological puzzle on some distant world. It is one of the deepest and most persistent enigmas in modern astrophysics, a vast, empty chapter in the biography of the cosmos itself. It is the mystery of the missing middler ghost in the gravitational machine, and our journey tonight is to hunt for that ghost, to fill that void, and to perhaps finally complete the story. To do so, we must first understand the two great dynasties we already know, the two titanic families of black holes that bookend this cosmic riddle. Our story begins not with a whisper, but with a shriek of cataclysmic violence. Imagine a star, a true leviathan of its stellar nursery, at least 25 times more massive than our own humble sun. For millions of years it has burned with a ferocious intensity, a celestial blowtorch fusing hydrogen into helium, and then helium into carbon, forging the heavier elements in its core, the very stuff of which you are made. It is a brilliant, defiant beacon against the endless dark. But this brilliance comes at a terrible cost. Its fuel is finite and its mass is its own worst enemy. Deep within its heart, the outward push of nuclear fusion has been locked in a titanic struggle with the inward pull of gravity. For its entire life, these two forces have maintained a delicate, furious equilibrium. Now the fuel runs out. The fire in the furnace sputters and dies. In less than a second, the stalemate is broken. Gravity, the universe's most patient and relentless force, wins. The star's colossal outer layers, now unsupported, come crashing down. They accelerate inwards at a quarter of the speed of light, slamming into the impossibly dense, newly formed core. The result is a rebound shockwave of unimaginable power, an explosion so luminous it can briefly outshine its entire home galaxy. A supernova. For a few brilliant weeks, it is a spectacle of cosmic creation seeding the interstellar medium with the elements needed for new stars, new planets, and perhaps new life. But what is left behind in the fading afterglow of this cosmic firework is something far more extreme, far more permanent. The core of that once great star, crushed beyond all known physics, continues to collapse in on itself. It shrinks past the point of a neutron star, past any boundary that matter as we know it can withstand. It collapses forever, pinching off a piece of space-time itself. What remains is a stellar mass black hole, a ghost of a star weighing perhaps 5, 10, 30, or on rare occasions approaching 100 times the mass of our sun. Its entire substance is compressed into a region of zero volume and infinite density, a singularity cloaked from our view by the event horizon, the ultimate one-way membrane from which not even light can escape. These are the commoners in the kingdom of black holes. They are born from a single definitive act of cosmic death. Throughout our own Milky Way, they drift by the millions dark predators silently stalking the stellar plains. Most are invisible lone wanderers, betrayed only by the subtle way their gravity bends the starlight of objects far behind them, a fleeting gravitational lens. But some are not alone. They are locked in a gravitational waltz with a companion star, a partner that survived the supernova blast. Here the black hole's presence becomes terrifyingly apparent. Its immense gravity acts like a cosmic siphon, pulling a stream of incandescent gas from its living companion. This stolen material doesn't fall straight in. Instead, it is whipped into a ferocious spinning accretion disk, a celestial maelstrom of superheated plasma. Friction and magnetic fields in this disk heat the gas to millions of degrees, causing it to blaze with high-energy X-rays. It is this scream of tortured matter, this final cry from the edge of oblivion, that allows our telescopes to find them. We see not the black hole, but its last violent meal. We have found dozens this way, these stellar vampires feasting in the dark. We can weigh them, measure their spin, and confirm their existence. They are the fundamental building blocks, the seeds of cosmic darkness, the tangible endpoint for the most massive stars in the universe. They represent one end of the known spectrum, the smaller, almost personal scale of gravitational collapse. They are the infants in our cosmic family portrait. But to find the other side of this family, the galactic patriarchs, we must pull our perspective far back from the death of a single star to the scale of galaxies themselves. Look towards the heart of nearly any grand galaxy you can find in the sky, from the majestic sweep of Andromeda to the swirling arms of the Whirlpool Galaxy. Look even deeper towards the glowing, star-choked centre of our own Milky Way, a place of frantic motion and unimaginable power. There at the gravitational nexus of it all, you will not find a star. You will not find a cluster of stars. You will find a monster of an entirely different order of magnitude. This is the realm of the supermassive black holes. These are not the ghosts of dead stars. They are the dark hearts of galaxies. They do not weigh tens or even hundreds of solar masses. They weigh millions, hundreds of millions, and in some cases tens of billions of times the mass of our Sun. Our own galaxy's central black hole, a relatively modest specimen named Sagittarius A, clocks in at over 4 million solar masses. All of that incomprehensible weight is concentrated at the galaxy's core, acting as the ultimate gravitational anchor. It is the celestial conductor of a vast cosmic orchestra. The galaxy does not orbit the supermassive black hole, but the black hole's immense gravity well dictates the chaotic high-velocity dance of the stars in the galactic core. For decades, their existence was merely a powerful theory, a necessary mathematical component to explain the furious motion of these central stars which whipped around an unseen centre at breathtaking speeds. To explain their orbits, there had to be something unimaginably massive and yet completely dark lurking there. Then we built telescopes powerful enough to see the effects directly. We tracked individual stars in our own galactic centre for years, watching them execute perfect Keplerian orbits around nothing. The only object that could command such loyalty, that could fit within the tight confines of those orbits, was a supermassive black hole. And when humanity linked telescopes across the globe to form one Earth-sized Eye the Event Horizon telescope, we did the impossible. We captured a shadow, a silhouette of darkness against a fiery ring of light, the portrait of the supermassive black hole at the heart of the galaxy M87, a titan weighing 6.5 billion solar masses. The evidence is now undeniable. They are real, and they are fundamental to the cosmos. They are not merely passive relics. When they feed, they can become the most luminous objects in the universe. As gas and stars spiral into their accretion disks, the energy released can be trillions of times brighter than our Sun. This is a quasar, a galactic nucleus so brilliant it can be seen from the very edge of the observable universe. The energy unleashed in this feeding frenzy is so potent it can launch jets of particles thousands of light years long, ploughing through the galaxy and profoundly influencing its destiny. A feeding supermassive black hole can regulate the birth of new stars, clearing out gas from the galaxy and effectively sterilizing it for eons. They are not just objects within galaxies. They are cosmic engines, sculptors of galactic evolution, the architects of cosmic structure. They are the undisputed patriarchs, the ancient kings on their gravitational thrones. And so the two great families are established. On one side, we have the stellar mass black holes, the commoners born from the explosive death of a single star, weighing in at a few dozen, perhaps up to 100 solar masses. On the other side, we have the supermassive royalty, the galactic anchors weighing millions to billions of solar masses, the infants and the colossal adults. And it is here, standing between these two well-documented populations, that we confront the unnerving silence, the gaping chasm in our understanding. Where is everything in between? Where are the black holes that weigh 500 solar masses, or 1,000, or 10,000, or 100,000? Nature as we understand it does not typically build in such disconnected leaps. Evolution, both biological and cosmic, favours gradual steps, a continuous spectrum of growth and development. We see fledgling stars, main sequence stars, and aging giant stars. We see dwarf galaxies, spiral galaxies, and giant elliptical galaxies. There is a continuity, a clear path of progression from small to large. Yet in the world of black holes, it is as if a crucial chapter has been torn from the book of cosmic creation. We have found a universe filled with newborns and ancient giants, but we are left to wonder where the adolescents are. This isn't just a trivial curiosity, it strikes at the very heart of how we believe the largest structures in the universe are assembled. The existence of billion solar mass black holes in the early universe is one of the most significant challenges in cosmology. How did they get so big so fast? A stellar mass black hole born in the universe's infancy simply cannot grow to a billion solar masses in the available time by slowly consuming gas and the occasional star. The numbers don't add up. It would be like trying to fill an ocean with an eyedropper. There must be a more efficient pathway, a faster growth track. The most elegant and logical solution to this profound cosmic puzzle is that there is another class of object we have been missing all along, an object that can bridge this impossible gap. Theorists have given them a name: intermediate mass black holes. These are the lost tribe, the missing link in black hole evolution. They are hypothesized to weigh from a few hundred up to a few 100,000 times the mass of our Sun, placing them perfectly within that vast silent desert between the stellar and supermassive populations. They would be the perfect cosmic stepping stones. Perhaps they form in the hearts of dense ancient star clusters, where dozens of stellar mass black holes and massive stars can merge in a runaway chain reaction. Or maybe they were forged from the direct collapse of massive gas clouds in the primordial universe before the first galaxies had even fully formed. However they are born, their existence would change everything. They could be the seeds, the gravitational kernels from which supermassive black holes grow. A galaxy could form around one of these intermediate objects, or multiple IMBHs could spiral together and merge at a galactic center, building up the supermassive titans we see today in a far more rapid and plausible way. They are the crucial ingredient that makes the cosmic recipe work. Without them, our theories of galaxy formation feel incomplete, hollow, and yet, for all their theoretical importance, they have remained maddeningly elusive. Finding them is exceptionally difficult. They're too small to dominate the center of a large galaxy like a supermassive black hole, making their gravitational influence subtle and hard to detect from afar. But they are also too massive to be formed from a single star, meaning they are unlikely to have a close stellar companion whose X-ray screams would betray their location. They lurk in the shadows in a mass range that makes them cosmic ghosts. This is the grand challenge, the epic quest we are now embarking upon. Our mission is to venture into this observational wilderness, to hunt for the faintest whispers and most subtle clues that might finally reveal the universe's hidden middleweights. We will search the hearts of globular clusters, those ancient dense cities of stars. We will scan the skies for flares of light from stars torn asunder by an unseen force. We will listen for the faintest gravitational ripples in space-time itself. The search is on. The evidence is mounting, and finding this missing link would not just fill a gap in a chart, it would illuminate the entire process of cosmic construction, revealing at last how the universe builds its greatest monsters. The hunt for the intermediate mass black hole has begun. What happens when a foundational story of the cosmos has a missing chapter? We thought we had mapped the lineage of creation's most enigmatic objects. On one side of the family tree you have the ghosts of giants. These are the stellar mass black holes born from the spectacular death throes of singular colossal suns. They are the violent punctuation marks at the end of a star's luminous sentence. Weighing in at a few dozen times the mass of our own sun, they are cosmic predators. Solitary, compact and voracious, they drift through the void, their presence betrayed only by the captured screams of unfortunate stars or the whisper of gravitational waves. They are born from a process we can model, a physics we can grasp. The life cycle is a drama in 3 acts: a star's brilliant life, its cataclysmic supernova death, and the final silent collapse of its core into a point of no return. This is a story with a beginning, a middle and an end we have witnessed. Then you turn your gaze to the other side of the cosmic ledger. Here in the sprawling incandescent hearts of virtually every major galaxy you find the titans, the supermassive black holes. These are not mere objects, they are gravitational monarchs, celestial anchors, around which entire star cities of hundreds of billions of suns perform a celestial ballet lasting billions of years. They are not measured in dozens of solar masses, but in millions, sometimes billions. Sagittarius A. The slumbering behemoth at the centre of our own Milky Way tips the scales at over 4 million suns. The monster in the galaxy M87, the first of its kind we ever directly imaged, is a staggering 6.5 billion solar masses. It's a weight so immense it warps the very fabric of space-time into a bottomless well, its shadow stretching wider than our entire solar system. And here, buried within this grand established narrative of the small and the colossal, lies the paradox. Here lies the gaping, unnerving void in our understanding. We had found the mice, and we had found the elephants. But for generations we could find absolutely nothing in between. No cosmic wolves, no celestial lions, just a silent, inexplicable chasm separating the two known kingdoms of black holes. This wasn't merely a small gap in the data, it was a profound logical inconsistency, a cosmic mystery that whispered of a fundamental piece of the puzzle we'd somehow entirely missed. The universe, it seemed, was hiding a secret, a missing link in the evolutionary chain of its most extreme creations. To truly feel the weight of this enigma, you have to journey back with us back to the final fiery moments of a star destined for greatness and oblivion. Imagine a sun at least 25 times more massive than our own. For millions of years it has been a titanic nuclear furnace, a brilliant sphere of incandescent plasma, held in a delicate, violent equilibrium. Deep within its core, the crushing force of its own immense gravity tries to collapse it. Pushing back is the ferocious outward pressure from nuclear fusion, a celestial blowtorch transmuting lighter elements into heavier ones, releasing staggering amounts of energy in the process. It is a lifelong war waged against itself, but this war cannot last forever. The star, like all stars, has a finite amount of fuel. As it ages, it burns through hydrogen, then helium, forging a layered onion-like core of progressively heavier elements: carbon, neon, oxygen, silicon. Finally, the furnace creates iron, and with iron the battle is lost. Iron is stellar ash. Fusing it consumes energy rather than releasing it. The outward pushing fire in the star's heart suddenly sputters and dies. In an instant, the equilibrium that defined the star for eons is shattered. With the furnace extinguished, gravity wins. It wins utterly and catastrophically. The star's core, an iron ball already denser than anything on Earth, collapses in on itself in less than a second. It implodes at a quarter of the speed of light, crushing protons and electrons together to form a hyper-dense ball of neutrons. This implosion triggers a rebound, a shockwave of unimaginable power that blasts outwards, meeting the star's still collapsing outer layers head-on. The resulting explosion is a supernova, an eruption so brilliant it can briefly outshine its entire host galaxy. It is one of the most violent events in the universe, a crucible that forges and scatters the heavy elements, the gold in your jewelry, the calcium in your bones across the cosmos, seeding the next generation of stars and planets. It is the ultimate act of cosmic recycling. But what of the core? What is left behind in the fading afterglow of this cosmic conflagration? If the original star was massive enough the crushed neutron core cannot hold, even the fundamental forces of nature cannot halt the final collapse. Gravity, relentless and absolute, squeezes the remnant down past any known state of matter, beyond the grasp of our physics. It crushes it down to a singularity, a point of infinite density. A stellar mass black hole is born. This story, for all its violence and grandeur, is comforting to scientists. It is a process governed by well-understood physics, a predictable outcome for the universe's most massive stars. We can observe the supernova remnants. We can detect the gravitational waves from merging black holes born this way. We can see them in binary systems siphoning gas from a companion star, creating accretion disks that glow fiercely in X-rays before the material takes its final plunge. We have their fingerprints. We know their origin story. There is a limit, however. The very process that creates them also caps their size. The most massive stars are so luminous, so violent that they blow away huge portions of their own mass in powerful stellar winds long before they ever go supernova. This cosmic sandblasting means that when they finally collapse, there's a natural ceiling on how much mass is left to form the black hole, typically no more than a few dozens, perhaps 100 solar masses at the absolute extreme. You simply cannot make 1,000,000 solar mass black hole this way. It's like trying to build a skyscraper out of a single bucket of sand. The raw materials just aren't there. So we turn our attention back to the galactic center, to the supermassive behemoths. If they weren't born from a single star, how did they come to be? The simple answer seems to be that they grew. They started small, and over the eons fed on a diet of gas dust and unlucky stars slowly accumulating mass. This is where the timeline of the universe delivers a devastating blow to that simple theory. Using our most powerful telescopes, we can look back in time. Light travels at a finite speed, so observing distant galaxies is like using a cosmic time machine, seeing them as they were when the light first began its long journey to us. And when we peer back into the dawn of the cosmos to a time just 700 or 800 million years after the Big Bang, we see something that should not exist. We see quasars. These are the most luminous objects in the universe galactic cores, blazing with the light of 1 trillion suns. This impossible brilliance is the death scream of matter being consumed by a supermassive black hole. The light from these quasars tells us that fully formed billion solar mass black holes were already in place when the universe was less than 1/10 of its current age. They were not just present, they were cosmic titans reigning over the first generation of galaxies. This is the timing problem, and it is a profound crisis for astrophysics. Starting with a seed from a dead star, a black hole would have to feed at the maximum possible rate continuously for billions of years to reach that size. There's a physical speed limit to this consumption, known as the Eddington limit. If a black hole feeds too quickly, the radiation blasted out by the superheated material in its accretion disk physically pushes away any more incoming fuel, effectively choking itself off. It's a cosmic self-regulation. The ancient quasars mock this limit. They show us behemoths that grew faster than our physics allows, reaching impossible sizes in an impossibly short amount of time. It would be like exploring a new continent and finding 1,000-year-old oak trees that, according to all known biology, could only have been planted a decade ago. It forces you to question the very origins of the seeds themselves. Maybe they didn't start from stellar mass black holes. Theorists faced with this paradox went back to their blackboards. The known methods were insufficient. Merging stellar mass black holes one by one would take far too long. The gravitational dynamics of such encounters are chaotic. More often than not, the merging objects would receive a powerful gravitational kick, flinging them out of their host galaxy altogether, not consolidating them at its centre. A new idea began to emerge, a whisper that became a hypothesis. What if the seeds weren't the tiny stellar mass objects we knew? What if the universe had a way to skip the first step? What if there was an intermediate class of black hole, a missing link that could form much larger and provide a more substantial starting point for supermassive growth? This theoretical object was the intermediate mass black hole, or IMBH. It was a phantom, a ghost in the machine of cosmic evolution, proposed not because anyone had seen one, but because its existence was required to make the rest of the story make sense. It was the perfect bridge across the chasm, weighing in at a few hundred to a few 100,000 solar masses. Large enough to grow quickly, but small enough to have formed through processes other than the direct evolution of a galactic core. But if they existed, where did they come from? Two extraordinary possibilities began to dominate the conversation, each painting a picture of a young universe far more violent and strange than we had imagined. The first scenario takes us into the heart of the most ancient and densely packed structures in our galaxy, globular clusters. These are breathtaking spherical swarms of hundreds of thousands, sometimes millions of stars, all born together in a single burst of creation billions of years ago. They are stellar cities, but with none of the comfortable spacing we see in our own galactic neighbourhood. Here stars are packed in 1,000,000 times more densely. Imagine a cosmic mosh pit, a gravitational demolition derby, where stars are constantly interacting, their orbits being twisted and torqued by near misses and close encounters. In this chaotic environment, a process known as mass segregation takes hold. Just as heavier rocks sink to the bottom of a shaken jar of sand, the most massive stars in the cluster inexorably sink toward its gravitational centre over millions of years. The core of a globular cluster becomes a pressure cooker, a crucible crowded with the most massive short-lived stellar giants. Here one of two things could happen. These massive stars could collide and merge, creating a single, unbelievably colossal superstar, which would then live a brief, furious life before collapsing into an intermediate mass black hole of several hundred solar masses. Alternatively, the massive stars could die their individual deaths, leaving behind a dense clutch of smaller stellar mass black holes. In the intense gravity of the cluster's core, these black holes would also sink, find each other, and begin a violent dance of death, a chain reaction of mergers, each collision birthing a slightly more massive black hole, until one grows dominant, clearing out its competitors and becoming a true IMBH. This was a plausible, if spectacularly violent pathway. But another theory, even more ambitious, reached further back in time. It proposed a genesis story from before the first stars had ever ignited. It imagined the universe in its absolute infancy, a time when there were no heavy elements, only vast, pristine clouds of hydrogen and helium gas left over from the Big Bang. Today, when a gas cloud collapses to form stars, it fragments into thousands of smaller clumps because heavy elements help the gas cool down efficiently. But back then, without those elements, the cooling process was incredibly inefficient. Theorists calculated that under very specific Goldilocks-like conditions, a primordial gas cloud of immense size, 100,000 solar masses or more, could collapse monolithically. It would not fragment into a cluster of normal stars. Instead, the entire colossal cloud would fall in on itself in one go, perhaps briefly forming a temporary quasi-star of unimaginable proportions before the whole structure collapsed directly entirely into a black hole. This was the direct collapse black hole model. It was a breathtaking idea. It meant that some of the universe's first monsters weren't born from the death of light, but from a dark genesis, from pristine gas that had never once been forged into a star. They would be born as IMBHs from the very start, perfect seeds ready and waiting, in the hearts of the first proto-galaxies perfectly positioned to begin the rapid feasting that would turn them into the supermassive quasars we see at the dawn of time. So the theories were in place. We had two compelling, elegant explanations for how these missing links might be forged. One in the chaotic hearts of stellar cities, the other in the silent purity of the cosmic dawn. Their existence would solve the timing paradox of the supermassive giants and fill the maddening gap in the black hole family album. There was just one monumental problem. For decades, we couldn't find a single one. The observational challenge was immense, a hunt for a creature that was by its very nature an expert at hiding. An IMBH is not a supermassive black hole. It doesn't sit at the center of a vast galaxy surrounded by a constantly replenished buffet of gas that makes it blaze as a quasar. It would likely be found in the core of a globular cluster, a region so blindingly dense with stars that picking out the signature of a single dark object within it is almost impossible. Or it might be the lonely monarch of a dwarf galaxy, a much smaller, fainter stellar system, where its gravitational influence would be subtle and hard to distinguish from a dense cluster of stars. They are dark, they are quiet, and they are small enough to be lost in the crowd. The search was on, but it was akin to listening for a single silent footstep in the middle of a roaring stadium. Their existence remained speculative, a beautiful and necessary theory that lacked the hard currency of observation. This phantom of the cosmos became a holy grail for a dedicated cadre of astronomers. They knew the story of the universe felt incomplete without it. They were convinced that this missing chapter was not gone, but merely hidden, written in an ink that was invisible to our existing methods. And so they began to devise new ingenious ways to see the unseeable, to prove that the universe's missing link was not a ghost after all. They would have to learn how to map the precise dance of individual stars searching for the telltale gravitational wobble caused by an unseen partner. They would have to search for the sudden, brilliant flare of a star torn apart by a tidal force no ordinary object could muster. They would have to push technology and their own ingenuity to the absolute limit, all in the hope of catching a fleeting glimpse of the universe's most elusive creature. For generations, the chasm in our cosmic census remained a ghost, haunting our theories, a silent indictment of our incomplete understanding. We had the stellar mass black holes, the savage remnants of colossal stars, and we had the supermassive titans, the gravitational anchors of entire galaxies. But the vital link between them, the adolescent stage of cosmic growth, was nowhere to be found. The question lingered in observatories and lecture halls across the planet. How do you find an object that is by its very nature the master of hiding? You cannot look for the object itself. You must look for the chaos it creates. You must search for the wreckage left in its wake. the tortured scream of matter being pushed past the breaking point. The hunt required a new kind of sight, a vision capable of piercing the veil of distance and dust to see the universe, not in the gentle shimmer of visible light, but in the most violent and energetic wavelengths imaginable. The dawn of this new era arrived in 1999, launched into the cold vacuum of space aboard the Space Shuttle Columbia. Its name was Chandra, a tribute to the great astrophysicist Subrahmanyan Chandrasekhar. More than a telescope, Chandra was a high-energy scalpel designed to perform astronomical surgery. Its exquisitely polished mirrors, a marvel of engineering, could focus X-rays, the light of cataclysm, with a precision 100 times greater than any instrument that had come before. For the first time, we could resolve the searingly hot, turbulent hearts of distant galaxies into collections of individual brilliant points of light. We were no longer looking at a blurry cityscape. We were suddenly able to read the street signs. And what we found almost immediately was a profound and exhilarating mystery. Dotted across the spiral arms and central hubs of neighbouring galaxies were sources of X-ray light so ferocious, so unbelievably powerful, they seemed to defy the known laws of physics. They were given a deceptively simple name, ultra-luminous X-ray sources, or ULX, but their nature was anything but simple. Imagine a stellar mass black hole, perhaps 10 or 20 times the mass of our Sun, feeding on a captured star. The material from that star spiralling into the abyss forms an accretion disk, a cosmic whirlpool of gas and dust heated to millions of degrees. As it glows, it shines, producing a torrent of X-rays. But physics imposes a strict fundamental speed limit on this process. It's a concept known as the Eddington limit. Think of it as a cosmic safety valve. The light pouring out from the hot gas exerts an outward pressure, a wind of pure radiation that pushes back against the very material trying to fall in. If a black hole tries to feed too quickly, the sheer brilliance of its meal literally blows the rest of the food away. A stellar mass black hole, no matter how voracious, simply cannot sustain a luminosity beyond a certain well-defined threshold. It is a line in the sand drawn by the fundamental forces of the universe. The ULX we were discovering with Chandra were not just crossing that line, they were obliterating it. They blazed with a radiance 10, 100, sometimes even 1,000 times brighter than the absolute maximum allowed for a typical stellar mass black hole. The light we were seeing was impossible. It was like finding a single lighthouse that outshined the combined light of an entire capital city. This was the first great clue, the tantalizing breadcrumb trail that led astronomers down a rabbit hole of intense debate and discovery. We were faced with a stark and thrilling dilemma, a cosmic fork in the road. Either our understanding of accretion physics was fundamentally wrong, or these were not stellar mass black holes at all. Perhaps hidden within the blinding glare of these celestial blowtorches, we were finally staring at the first direct evidence of the missing link. The astronomical community quickly fractured into two opposing camps, each championing a different explanation for these baffling phenomena. The first and most sensational hypothesis was that ULX were precisely what we had been searching for. They were the unambiguous signposts of intermediate mass black holes. The logic was beautifully, compellingly simple. The Eddington limit, that cosmic speed limit on brightness, is directly tied to the mass of the central object. A more massive object has a stronger gravitational grip, allowing it to hold onto its food and burn brighter before the radiation pressure becomes overwhelming. A black hole of, say, 1,000 solar masses would have an Eddington limit 100 times higher than a 10 solar mass black hole. The impossible luminosity of a ULX suddenly becomes perfectly natural, even expected, if the engine at its heart is not a stellar pipsqueak, but a genuine intermediate mass leviathan. For this camp, the case was nearly closed. Each new ULX discovered was another potential specimen, another piece of a cosmic puzzle falling neatly into place. They believed they were mapping the habitats of these long-sought-after beasts, charting their distribution across the local universe. But science thrives on skepticism, and a second, more cautious camp soon emerged, armed with an alternative and deeply clever explanation. They argued that we didn't need to invoke a whole new class of black hole to solve the ULX problem. Instead, they proposed that we were being fooled by an exotic cosmic illusion. Their theory centered on the idea that under very specific circumstances, a regular run-of-the-mill stellar mass black hole could appear to break the Eddington limit. One way this could happen is through a process called geometric beaming. Imagine the black hole's accretion disk isn't a simple flat plate. What if, due to extreme magnetic fields or the sheer speed of its rotation, it funnels its energy into two powerful, tightly focused jets, like the beams of a searchlight? If one of those jets happened to be pointed directly at Earth, the source would appear astoundingly artificially bright to us, while an observer looking at it from the side would see nothing out of the ordinary. We would be catching the full fury of its emission in a concentrated beam, radically overestimating its true total energy output. It would be a trick of perspective, a cosmic sleight of hand. Another even more complex idea involves something called supercritical accretion. This theory suggested that under a relentless barrage of infalling matter, the accretion disk itself could transform. Instead of a thin, elegant whirlpool, it might puff up into a thick, donut-shaped structure, a chaotic maelstrom of gas that could trap some of its own radiation and channel the rest out through a vortex-like funnel. This slender disk model provided a physical mechanism for a stellar mass object to punch through its theoretical ceiling, sustaining a luminosity far greater than what the classical Eddington model would permit. The debate became fierce, a high-stakes intellectual battle, fought in the pages of scientific journals and at international conferences. On one side, you had the elegant simplicity of the IMBH hypothesis. On the other, the complex but plausible physics of the superaccretion and beaming models. The universe was presenting us with a crime scene, a source of impossible energy, and two completely different culprits. One was a giant leaving proportionately giant footprints. The other was a much smaller suspect, but one who had found a way to use an exotic, highly focused weapon. To break the stalemate, we had to move beyond simply measuring the brightness of the light. We needed more data, different kinds of data. We had to find a way to peer through the glare of the ULX and interrogate the central engine directly. The search expanded, diversifying its methods and employing the full arsenal of modern astronomy. If some ULX were indeed powered by stellar mass black holes firing relativistic jets, then those jets should produce more than just X-rays. As they blasted through the interstellar medium at nearly the speed of light, they should generate powerful shock waves, creating distinctive bubbles of radio emission. This prompted a new campaign, bringing in the power of radio interferometry. Arrays of radio telescopes like the Very Large Array in New Mexico were turned towards the most prominent ULXs. Their combined power allowed astronomers to create images with razor-sharp resolution, sensitive enough to detect the faint radio whispers that might betray the presence of a jet. The hunt was painstaking. In some cases, faint extended radio structures were found lending credence to the beaming hypothesis for at least a subset of these objects. But for many others, the radio silence was deafening. There were no jets, no radio bubbles, just the overwhelming glare of X-rays. These silent sources became the prime candidates, the most promising contenders for genuine intermediate mass black holes. The evidence was tipping, but not decisively. Another clue, however, pointed the search in a completely new direction, not just to a new kind of object, but to a new kind of environment. Astronomers began to notice that a significant number of ULX were not found randomly scattered throughout their host galaxies. Instead, they appeared to be preferentially located in very specific, very ancient and very crowded neighborhoods, globular clusters. Globular clusters are magnificent, almost magical objects. They are ancient spherical swarms of hundreds of thousands, sometimes millions of stars, all bound together by their mutual gravity. Older than the spiral arms of the galaxies they orbit, these clusters are cosmic fossils, relics from the universe's infancy. They are also among the most densely packed places in the cosmos. In the core of a globular cluster, stars are not isolated points of light separated by vast emptiness, as they are in our own galactic vicinity. They're crammed together, swinging past one another in a frantic, relentless gravitational dance. This stellar beehive is the perfect crucible for creating monsters. The sheer density makes collisions and close encounters not a remote possibility, but an inevitability. Stars can be stripped of their outer layers, binary systems can be disrupted, and black holes formed from the cluster's first generation of massive stars can sink like stones toward the gravitational centre. This is where the theory of runaway collisions comes into play. In the hyperdense core of a globular cluster, a black hole could begin a chain reaction of mergers. It would swallow another black hole growing in mass, and its increased gravitational pull would make it an even more effective predator. It would then capture and consume another and another in a cascade of gravitational violence that could over billions of years build a stellar mass object up to intermediate scale. A globular cluster, therefore, isn't just a city of stars, it's a potential factory for IMBHs. The discovery of powerful ULX residing right in the heart of these ancient clusters was a bombshell. It was circumstantial evidence, yes, but it was powerfully suggestive. It placed a suspected culprit squarely at the scene of a plausible crime. Suddenly, these dense, glittering star cities became primary hunting grounds in the search for the missing link. Observing the core of a globular cluster is an immense technical challenge. You're trying to find the subtle influence of a single dark object amidst the blinding glare of 1 million suns packed into a space only a few light years across. It required astronomers to develop entirely new techniques. They began meticulously tracking the motions of individual stars near the cluster's centre, using the Hubble Space Telescope and powerful ground-based observatories equipped with adaptive optics to correct for the blurring of Earth's atmosphere. The logic was the same as that used to prove the existence of the supermassive black hole in our own galaxy's core, just on a much more difficult scale. If an intermediate mass black hole was lurking at the centre, its gravity should act like an invisible shepherd, subtly accelerating the stars that swung closest to it. Finding that subtle uptick in stellar velocities, that tiny gravitational fingerprint would be the smoking gun. So the search had evolved. It began with a single perplexing clue: the impossible brightness of ULXs. It grew into a fierce debate between competing physical models, a battle of ideas that pushed the boundaries of theoretical astrophysics. And it had now transformed into a multi-pronged observational assault employing our most advanced tools to scan the skies in different wavelengths and to dissect the most extreme environments the universe has to offer. We were sifting through the glare of distant galaxies, eavesdropping on the radio whispers of cosmic jets, and meticulously tracking the ballet of ancient stars in dense, glittering clusters. The mystery of the missing link was no longer just a gap in a chart. It had become a tangible quest. The candidates were being identified, the hiding places were being narrowed down, and the methods for their unmasking were growing more sophisticated by the day. We hadn't found our quarry yet, but for the first time we could truly sense it was close. The scent was on the wind, the hunt was on. For generations the search had been a story told in whispers and shadows. We hunted for our missing links in the faint, furtive wobbles of distant stars, in the strange accelerated dance of dense globular clusters, and in the enigmatic flares of ultra-luminous X-ray sources. The evidence was tantalizing, a trail of cosmic breadcrumbs scattered across the void, yet it was always indirect, always circumstantial. We were like detectives at a crime scene with fingerprints, but no suspect, a motive with no culprit. We could infer the presence of these intermediate mass ghosts. We could model their gravitational haunting of their stellar neighbourhoods, but we could never truly see them, never truly prove their existence beyond a reasonable doubt. The universe, it seemed, was content to keep its middleweights hidden, leaving a frustrating gaping hole in our grand tapestry of cosmic evolution. But all of that was about to change because humanity was on the verge of developing an entirely new sense. What if after a century of staring into the cosmic dark we could finally learn to listen? What if we could hear the silent symphony of gravity itself, the tremors in space-time that Einstein had predicted but believed we could never detect? This was not an act of listening for sound, which needs a medium to travel. This was an endeavour of almost unimaginable delicacy, an attempt to feel the very stretching and squeezing of reality as a gravitational wave passed by. The instruments we built for this task, the laser interferometer, gravitational wave observatories or LIGO, were marvels of terrestrial engineering designed to perceive the most violent events in the cosmos. In Washington State and Louisiana, we constructed two identical L-shaped leviathans, their 4-kilometre-long arms encased in the world's most perfect vacuum tubes. Down these tunnels we would fire pristine laser beams, reflecting them off mirrors so perfectly polished that if one were the size of a continent, its largest imperfection would be no bigger than a grain of sand. The beams from each arm would meet, and under normal conditions cancel each other out, in a process called destructive interference, leaving only darkness at the detector. But if a gravitational wave, a ripple from some distant cataclysm, were to wash over the Earth, it would minutely stretch one arm of the detector while squeezing the other. This infinitesimal distortion, a shudder 1,000th the diameter of a single proton, would knock the laser beams just slightly out of perfect alignment. For a fleeting instant, the darkness would flicker into light, a signal of a disturbance not on Earth, but in the fundamental structure of the universe itself. For years, the detectors listened in profound silence, a planetary-scale microphone attuned to a frequency no one was certain we would ever hear. Then, on September 14, 2015, the silence was broken. From a distant galaxy, 1.3 billion light-years from home, a vibration arrived. It was the echo of a final violent embrace between two black holes, each about 30 times the mass of our Sun. As they spiraled towards their doom, they churned space-time into a tempest, sending out a crescendo of gravitational waves. The signal, when converted to sound, was a simple, rising chirp lasting less than a quarter of a second. But in that whisper, a revolution was born. We had heard the sound of space-time ringing like a drum. Einstein was right. And more importantly, we now had a new, unambiguous way to witness the universe's most extreme phenomena. In the years that followed, LIGO, soon joined by its European counterpart Virgo, began to build a catalogue of these cosmic collisions. We heard the mergers of neutron stars, the cataclysmic forges that create the universe's heavy elements like gold and platinum. We heard the merging of dozens of stellar mass black holes, filling in the sensors of these common cosmic predators. Each detection was a triumph, a new note in the symphony of the gravitational universe. We were learning the language of space-time, but the specific dialect we were desperate to hear the signature of an intermediate mass black hole remained elusive. The ghosts were still silent. That is until May 21st, 2019. On that day, a signal of a completely different character washed over the detectors. It was not the elegant rising chirp we'd grown accustomed to. This was something else entirely. It was a brutish, convulsive shudder of space-time, a signal so short and powerful it was almost mist, lasting barely a tenth of a second. It was less a chirp and more a deep, resonant thump, as if a cosmic giant had slammed a door at the edge of observable reality. The signal, officially designated Q90521, was incredibly faint, buried deep within the noise of the detectors, but it was unmistakably present at all three observatories. And when physicists began to deconstruct this phantom sound, they realized they were looking at something that defied their expectations, something that broke the established rules. The frequencies were lower, the duration was shorter, and the implied power was staggering. Whatever had produced this gravitational scream was unlike anything we had ever heard before. It spoke of entities far more massive, locked in a far more violent and rapid collision than the stellar mass pairings that had become our baseline. The brief guttural cry of G1F21 suggested that we had finally stumbled upon the lair of true monsters. To understand the nature of the event, scientists had to work backwards, using the precise shape of the wave to model the objects that created it. The task was akin to reconstructing two colliding bells, by listening only to the sound of their final shattering chime from across a vast ocean. And the answer that emerged from the supercomputer simulations was profoundly strange, presenting a paradox wrapped inside a mystery. The gravitational wave had been produced by the merger of two enormous black holes. The first, the primary partner in this deadly dance, weighed in at an estimated 85 times the mass of our Sun. The second was a staggering 66 solar masses. Immediately, alarm bells went off in the astronomical community. These numbers were not just big, they were supposedly impossible. According to our best models of stellar evolution, there exists a forbidden zone for black holes, a desolate region known as the pair instability mass gap. We believe that stars massive enough to produce black holes between roughly 65 and 120 solar masses do not collapse quietly into darkness. Instead, in their death throes, their cores become so hot that they generate vast quantities of matter and antimatter. This process triggers a runaway thermonuclear explosion so violent that it completely obliterates the star, leaving no remnant at all. No black hole, no neutron star, nothing but expanding gas and dust. Yet here was GW190521, an event apparently caused by at least one, and possibly two black holes dwelling squarely within this forbidden wasteland. It was a confounding puzzle. Where could such impossible objects have come from? The universe was not supposed to make them. A thrilling yet controversial possibility began to take shape. Perhaps these progenitor black holes were not born from the collapse of single solitary stars. Perhaps they were second-generation entities themselves, the product of previous unobserved black hole mergers. In the chaotic, densely packed heart of a globular cluster or a young massive star cluster, smaller black holes could have collided and merged over eons, gradually building up their mass. A 30 solar mass black hole could merge with a 40 solar mass black hole, creating a new 70 solar mass object, a black hole, that could not have formed from a star but could be built through this process of hierarchical merger. GW190521 might not have been a single isolated event, but the culmination of a long and violent family history, a chain of gravitational cannibalism stretching back through cosmic time. We were potentially witnessing a key mechanism in the cosmic food chain, the process by which black holes grow, evolve and climb the ladder of mass. But the true revelation, the discovery that would send shockwaves through the entire field of astrophysics, was not what these two black holes were, it was what they became. The final moments of the merger encoded in that fleeting gravitational thump described a cataclysm of unimaginable proportions. Occurring some 7 billion years in the past when the universe was only half its current age, these two impossible titans finally surrendered to their mutual gravitational pull. In the last fraction of a second, as they spiraled together at more than half the speed of light, they warped the very fabric of existence into a violent vortex. The collision itself was not an explosion of matter and light, but a silent, pure conversion of mass into raw energy, broadcast across the cosmos as gravitational waves. The peak power of that single moment of that final instantaneous union was 50 times greater than the combined light of every single star in the entire observable universe. It was the most powerful event humanity has ever detected since the Big Bang itself. All of this awesome universe-shaking power was unleashed to announce the birth of a single new object. After the space-time storm subsided, and the universe in that location returned to a silent, stable curvature, a new black hole had been forged in the crucible of the collision. To find its mass, scientists performed a simple but profound calculation. They added the masses of the two parent black holes, 85 and 66 solar masses, and then subtracted the mass that had been radiated away as the pure energy of gravitational waves. That energy, according to Einstein's EMC2, was equivalent to nearly 8 entire solar masses vaporized into space-time ripples in an instant. The final sum, the mass of the black hole left behind, was 142. 142 times the mass of our Sun. The number hung in the air, a testament to the awesome power of the cosmos. 142 solar masses. It was not a stellar mass black hole born from the collapse of a star. It was far too large. It was not a supermassive black hole, the galactic anchors weighing millions or billions of suns. It was far too small. It landed squarely, irrefutably, undeniably in the heart of the desert in the very mass range we had sought for decades. It was an intermediate mass black hole. For the first time, we had not just inferred the existence of one of these creatures from its subtle influence on its surroundings. We had not seen its shadow or its echo. We had witnessed its birth. We had a recording of its genesis, a birth certificate written in the language of gravity itself. The ghost story had ended because the phantom had finally audibly materialized before us. GW190521 was more than just another detection. It was a profound paradigm shift. It was the discovery of a new species in the cosmic zoo, the missing link we had hunted for so long. And it did more than just prove that IMBHs exist. It showed us with stunning clarity one definitive way they can be made. They can be built piece by piece through the merger of smaller black holes. This hierarchical assembly model, once a compelling theory, now had its first piece of direct, unambiguous observational evidence. The implications were breathtaking, rippling outwards through nearly every branch of cosmology and astrophysics. These IMBHs were no longer a theoretical convenience, but a proven component of the cosmic architecture. Suddenly, the strange motions within globular clusters made more sense. They were likely being choreographed by a central IMBH, created through exactly this kind of merger process. The ultra-luminous X-ray sources too bright for any stellar mass object now had a confirmed culprit. More profoundly, this discovery provided the first solid rung on the ladder that connects the small black holes born from stars to the supermassive behemoths that dictate the fate of entire galaxies. Perhaps the seeds of those galactic monsters were not exotic objects from the dawn of time, but IMBHs like the one born from G-Bar 905221, which grew over billions of years through a steady diet of stars gas and other black holes. The universe suddenly seemed more orderly, the great chain of being more complete. The chasm in our understanding had not just been bridged, it had been filled by the violent creation of a 142 solar mass titan, 7 billion light-years away. The hunt for a single IMBH was over, but the discovery had blown the doors wide open for 1,000 new questions. Now that we have found one, how many more are out there lurking silently in the dark? What role have these celestial middleweights played in sculpting the galaxies we see today? And what other secrets will be revealed now that we have finally taught ourselves how to listen to the whispers of gravity? And so, for a fleeting, almost imperceptible moment, the universe had whispered its secret. That ephemeral chirp, the sound of GPU 199, 5421 was more than just a discovery, it was a vindication. Across the globe, in control rooms and university offices, a collective breath was released. The hierarchical merger model, the elegant step-by-step story of cosmic growth had found its triumphant proof. The idea that black holes could climb a gravitational staircase, that stellar mass corpses could waltz together, merge, and give birth to a larger heir was no longer just a compelling theory. We had heard the birth cry of an intermediate mass black hole forged in the crucible of a final violent union. It was a beautiful, tidy solution to a decades-old puzzle. The missing link, it seemed, had been found, and its origin story was one of patient cosmic cannibalism written in the language of space-time itself. The narrative felt complete, the chapter seemingly closed, but science rarely, if ever, offers such simple closures. A triumphant discovery upon closer inspection often reveals itself not as a destination, but as a gateway to a landscape of far deeper and more bewildering questions. The very clarity of GW1900521 signal, its unambiguous testimony to a merger, began to cast long shadows over our assumptions. Yes, this pathway to the IMBH kingdom was real. We had the evidence, a gravitational ghost captured in our detectors, but was it the only path? Was this elegant, gradual ascent the sole method the cosmos employed to build its mid-sized monsters? The universe, we were beginning to suspect, is rarely so creatively constrained. In answering one question, we had inadvertently thrown open a Pandora's box of possibilities, revealing that the hunt for the missing link was not over. In fact, it had just fractured into multiple parallel investigations, each searching for a different species of beast. Suddenly, we were not just looking for one missing link, but for an entire hidden lineage, a diverse family of IMBHs with wildly different birthrights. The hierarchical merger model, for all its validated elegance, began to look like just one chapter in a much grander, more complex epic. Scientists were forced to revisit older, more exotic theories, ideas once relegated to the fringes of computational models, now thrust back into the spotlight by our newfound knowledge. The cosmos, it turned out, might have more than one recipe for creating these gravitational titans. The tidy staircase we had celebrated might be accompanied by express elevators and violent, chaotic scrambles to the top. The debate was reignited, fueled not by a lack of evidence, but by the profound implications of the evidence we finally held. We'd found a way, but the universe might have many. Imagine for a moment the infant cosmos. Not the universe of today, filled with intricate galaxies and seasoned with heavy elements forged in generations of stars. Go back further to a time of profound simplicity and terrifying scale. A time just a few 100 million years after the Big Bang, when the only ingredients available were vast, pristine clouds of hydrogen and helium gas. this primordial nursery, the rules of star formation were different. Today, as a gas cloud collapses, heavier elements like carbon and oxygen act as efficient coolants, allowing the cloud to radiate away heat fragment and form hundreds or thousands of individual relatively small stars. But back then, in that pure, untainted environment, these crucial cooling agents simply did not exist. A colossal cloud of primordial gas 1,000,000 times the mass of our Sun would have no such braking mechanism. As gravity pulled it inexorably inward, its internal temperature would skyrocket, creating immense pressure that resisted fragmentation. The cloud would be unable to shatter into a litter of normal stars. Instead, it would remain terrifyingly coherent, a single monolithic entity caught in a runaway gravitational collapse. The entire gargantuan structure, containing enough matter to build a small galaxy, would plummet inward upon itself in a cataclysm of unimaginable proportions. It wouldn't ignite as a star. It was far too massive, its own gravity too overwhelming. It would bypass the stellar stage of life entirely. This was not starbirth. This was a celestial stillbirth, a direct and brutal shortcut on the cosmic food chain. This is the heart of the direct collapse model. It proposes a lineage of IMBH that are not built but born. They spring into existence fully formed as primordial titans weighing tens of thousands of solar masses without ever having been a star, without a single merger. They are the old blood, the ancient nobility of the black hole family tree forged in the unique crucible of the dawn of time. Finding one would be like discovering a living dinosaur, a relic from a bygone era, with a completely different evolutionary history. These direct collapse black holes, or DCBHs, would be a fundamentally different flavour of monster. They wouldn't be the product of a long and violent adulthood spent consuming their peers. They would be born as giants, their immense mass a birthright conferred by the unique physics of the universe's infancy. The existence of such beings would dramatically alter our understanding of cosmic evolution, providing a ready-made seed to explain the impossibly large supermassive black holes we see shining as quasars when the universe was less than 1 billion years old. It would mean that from the very beginning the cosmos was building giants. But the universe's creative potential for violence and construction doesn't end there. If the direct collapse model offers a pathway of immense scale and primordial simplicity, a third theory presents a vision of pure, unadulterated chaos. To understand it, we must leave the pristine emptiness of the early universe and travel to a different kind of extreme environment, one that can still be found today, the heart of a globular cluster. These are ancient, breathtakingly dense cities of stars where hundreds of thousands, sometimes millions of suns are packed into a sphere just a few dozen light years across. If you were on a planet inside one, your night sky wouldn't be black. It would be a blinding, continuous blaze of starlight with thousands of stars appearing brighter than the full moon. The gravitational environment here is not a gentle waltz. It is a frantic, violent mosh pit. In the hyper-congested core of such a cluster, stars are not isolated points of light. Their orbits are chaotic, their gravitational interactions constant and unforgiving. Here the theory of runaway stellar collisions comes into play. It begins with the most massive stars in the cluster. Due to a process called dynamical friction, they sink towards the gravitational center like heavy stones in a shaken box of sand. The core becomes a pressure cooker of massive volatile stars. Close encounters that would be astronomically rare in the sparse suburbs of the Milky Way happen here constantly. Stars are flung into one another in a celestial demolition derby. A large star might merge with a smaller neighbour, becoming even more massive and gravitationally dominant. This makes it an even bigger target, an even more effective predator. A chain reaction begins. This newly engorged star, a blue supergiant of unimaginable proportions, barrels through the cluster's core, its gravity pulling in and consuming other stars in a frantic runaway process. One collision leads to another, the star growing catastrophically, with each merger becoming a bloated, unstable behemoth 1,000 times the mass of our Sun. This stellar pile-up cannot last. The colossal composite star, forged from the bodies of its siblings, quickly exhausts its fuel and collapses under its own immense weight. It does not go supernova in a conventional sense. Its gravity is too extreme. It implodes, directly forming an intermediate mass black hole in a single convulsive event born from sheer kinetic violence. This IMBH, a product of a frantic localized feeding frenzy, is a creature of its environment. Its story is not one of primordial grandeur or patient mergers over eons, but of a short, brutal life of relentless consumption in the most extreme stellar environments imaginable. So the stage is set. We have not one, but three compelling narratives for the origin of the same object. The patient architect assembling an IMBH piece by piece through hierarchical mergers. The primordial sculptor creating a giant from whole cloth in a direct collapse. And the chaotic brawler forging a monster in the heart of a stellar demolition derby. GW 1905-21 proved the first story is true, but the other two remain tantalizing unproven possibilities. The new grand challenge for astrophysics is therefore not just to find more IMBHs, but to become cosmic detectives to learn how to distinguish these different flavors of darkness from one another. How can we look at a black hole, an object that by its very nature reveals almost nothing, and deduce its life story? The answer lies not in looking at the black hole itself, but at the clues it leaves behind the fingerprints on the cosmic crime scene. Each formation channel, each recipe, should produce a black hole with a subtly different set of characteristics, a unique forensic signature. An IMBH born from the merger of two smaller black holes like G90521 should be a wild beast. The final moments of its creation are a maelstrom of spiraling space-time, a violent event that imparts a tremendous amount of angular momentum. We therefore expect these merger-born IMBHs to have very high spins whirling like furious gravitational gyroscopes. Furthermore, the emission of gravitational waves during the merger is not perfectly symmetrical. This asymmetry can deliver a powerful kick to the final black hole, launching it like a cannonball at hundreds or even thousands of kilometers per second. Consequently, we might expect to find these IMBHs not in the center of their host galaxies, but wandering the lonely galactic halos exiled from their birthplace by the very violence of their creation. A fast-spinning solitary IMBH is a prime suspect for a hierarchical merger origin. A direct collapse black hole, on the other hand, should carry the signature of its pristine ancient birth. Since it was born from a single relatively orderly collapse of a non-rotating or slowly rotating gas cloud, its spin should be significantly lower. It would be a more sedate, tranquil giant. But the most telling clue would be its environment. These objects could only form in the primordial universe before the cosmos was polluted with heavy elements. Therefore, we must search for them in the most chemically primitive, undeveloped galaxies we can find. We must look for them in ultra-faint dwarf galaxies, tiny ghostly collections of ancient stars that have remained largely untouched since the dawn of time. Finding an IMBH with a low spin sitting quietly at the heart of one of these cosmic fossils would be powerful evidence for the direct collapse model. It would be a living relic, its very existence a testament to a different set of physical laws in the infant universe. And what of the monster from the stellar mosh pit? The product of runaway collisions, its defining characteristic would be its home. It must reside or have originated in the exact center of an incredibly dense old star cluster. Its presence would have sculpted its surroundings. We would expect to see a strange distribution of stars around it, a cusp in brightness, or its gravity has hoarded a retinue of stellar companions. We might also see evidence of the past carnage, an unusual population of blue straggler stars formed from less extreme collisions, or a deficit of the massive stars that were consumed to create the black hole in the first place. The environment itself would be the smoking gun. The IMBH would be the king of a gravitational monarchy, its very existence inseparable from the chaotic, crowded court of stars that both birthed it and now serves it. The cluster's unique structure would be an indelible fingerprint screaming of a violent collisional past. This quest to differentiate between the potential origins of IMBHs is far more than an academic exercise in taxonomy. It strikes at the very heart of one of the greatest mysteries in all of cosmology, the growth of their larger cousins, the supermassive black holes that sit enthroned at the center of nearly every major galaxy, including our own Milky Way. These behemoths, weighing millions or billions of solar masses, pose a profound timing problem. We see them shining as brilliant quasars in the very early universe, at a time when there simply doesn't seem to have been enough cosmic history for them to have grown so large one stellar mass meal at a time. It's like finding a fully grown redwood tree just 1 year after the seed was planted. It demands a faster, more efficient growth mechanism. This is where the different flavours of IMBHE become critically important. They are the seeds from which these supermassive black holes must have grown. And the nature of the seed determines the entire subsequent life of the tree. If most IMBHs are formed through the slow, patient process of hierarchical mergers, then the timing problem for supermassive black holes becomes even more severe. It's a slow path to building a seed which leaves even less time for that seed to grow into a monster. But if the universe was peppered with direct collapse black holes from the very beginning, born as heavy seeds of 10,000 solar masses or more, the problem vanishes. These ready-made giants would provide a crucial head start, allowing supermassive black holes to balloon to their observed sizes quickly and easily in the early cosmos. The prevalence of this one specific IMBH flavour could single-handedly solve the riddle of the ancient quasars. We have moved beyond a simple search for a missing link. We have uncovered the possibility of a vast, tangled and wonderfully complex family tree for black holes. A tree with different branches, different lineages, each shaped by the unique conditions of its corner of the cosmic forest. The placid giants born in primordial clouds, the chaotic brawlers from stellar cities, and the patient cannibals built from the wreckage of their kin. Each one tells a different story about the universe's capacity for creation and destruction. The revelation of Gibiofantas Svevututu did not give us the final answer. Instead, it gave us the right questions to ask, transforming our search into a far richer, more nuanced and more profound investigation. The task now is to map this hidden genealogy, to understand which pathways dominate, and to finally reveal the full intricate story of how the universe builds its great engines of gravity from the missing links to the colossal titans that shape the galaxies we call home. For so long, the search has felt like a whispered ghost story, told by astrophysicists in the quiet hours of a long night. We had found tantalizing clues, spectral phantoms and gravitational tremors that hinted at something lurking in the shadows between the known worlds of black holes. Each piece of evidence was a puzzle in itself, compelling, yet incomplete, a single photograph of a creature no one had ever truly seen. Now, standing at the precipice of understanding, we watch as those scattered, lonely clues begin to find each other drawn together by an undeniable truth. The whispers are becoming a roar, the isolated snapshots emerging into a breathtaking panoramic view of a new cosmic reality. This is the moment the case is broken, when threads of inquiry woven independently through space-time finally converge into an irrefutable tapestry of discovery. The first definitive chord in this new symphony of understanding was struck not by light, by the very fabric of space-time itself. The gravitational wave observatories we built to listen for the universe's most violent secrets had already delivered the songs of merging stellar mass black holes, their final frantic chirps of inspiration. But then a new sound began to emerge from the noise, a deeper, more resonant tone that spoke of a different class of collision altogether. It was a lower frequency rumble, a slower, more deliberate spiral of two immense objects whose masses defied easy explanation. These were not the 30 solar mass beasts we had grown accustomed to. The data screamed of objects weighing hundreds, even thousands of times the mass of our sun, locked in a final gravitational embrace. One event, then another, and then a steady, undeniable cadence of detections began to paint a startling picture. These were not anomalies, they were a population. Each new signal arriving from the unfathomable depths of cosmic history was another voice joining the chorus, confirming that intermediate mass black holes did not just exist, but that they were actively, violently shaping the cosmos. Listening to these waves, you are hearing the universe's own census, a direct accounting of its hidden giants. You're hearing the sound of the missing link forging itself into existence, a process repeated countless times across the eons, a fundamental mechanism of cosmic growth we were finally privileged to witness. The waves carry the precise masses, the spins the exact energy released in a flash of gravitational fury, leaving nothing to interpretation. This was not inference. This was a direct, unambiguous measurement, a gravitational fingerprint of the very monsters we had sought for so long. While space-time itself was singing of their existence, a different kind of investigation, one steeped in the most energetic light in the universe, was reaching its own dramatic conclusion. For years, our X-ray telescopes orbiting high above the distorting veil of Earth's atmosphere had been staring into the blazing hearts of distant galaxies and the dense cores of globular clusters. They were hunting for the telltale signature of matter in its death throes, superheated to millions of degrees as it spirals into a black hole's accretion disk. This cosmic blowtorch, a swirl of incandescent plasma, is one of the most luminous phenomena in the universe. Yet the light it emits is a precise forensic tool. The temperature of the disk, the speed of its rotation, and the flickering variability of its X-ray output are all dictated by the mass of the central engine driving it. A stellar mass black hole, with its compact event horizon, creates a ferociously hot, rapidly changing disk. A supermassive black hole, by contrast, governs a cooler, more stable, and vastly larger accretion structure. For decades, we saw only these two extremes, but with more advanced instruments and sophisticated analytical models, we began to detect a strange new class of X-ray sources, a family of celestial beacons that fit neither category. These were the ultra-luminous X-ray sources, or ULX objects, shining with a terrifying intensity that should have been impossible for any known stellar mass object to produce without tearing itself apart. For a time, they were a profound mystery celestial outliers that broke our models. Some proposed they were ordinary black holes beaming their radiation toward us in a tight jet, creating an illusion of power. Others suggested more exotic physics were at play. But as the data accumulated, a more elegant and powerful explanation gained ground, one that perfectly aligned with the emerging gravitational wave evidence. These ULX were not illusions. They were exactly what they appeared to be: accretion disks radiating with an intensity perfectly proportional to a central object of several hundred to many thousands of solar masses. They were the beacons of feeding intermediate mass black holes. We could see it in the specific spectral signatures imprinted on the light, these subtle shifts in energy caused by gas orbiting at incredible speeds, deep within the gravitational well. These were not the chaotic flickers of a small black hole, nor the stately grandeur of a supermassive one. They displayed a unique intermediate pattern of variability, a distinct rhythm that was the telltale heartbeat of this missing class. We were no longer just inferring their presence, we were watching them feed. In the distant cores of starburst galaxies and within the crowded confines of ancient star clusters, these X-ray confessions revealed IMBHs, actively consuming their surroundings, flaring into brilliance as they swallowed a hapless star or a dense cloud of interstellar gas. Each flare was a scream in high-energy light, a confirmation written in plasma and radiation, telling the very same story the gravitational waves were telling through the vibrations of space-time. The universe, it turned out, was using two entirely different languages to announce the same fundamental truth. The evidence was becoming overwhelming, a pincer movement of observation closing in on the mystery from two different directions. One method captured their violent birth in mergers, the other captured their sustained life as they fed. Together they formed a powerful, self-reinforcing loop of confirmation, transforming a decades-old hypothesis into an observed and verifiable fact. Yet even this powerful combination of evidence was not the final word. The third and perhaps most elegant line of inquiry came from a far quieter, more patient form of cosmic observation. It came from the gentle art of watching stars dance. For over a century, astronomers have been captivated by globular clusters, those ancient glittering spheres of stars that orbit the Milky Way and other galaxies, like a swarm of cosmic bees. These clusters are among the oldest structures in the universe, dense, self-contained cities of 1 million stars packed into a space only a few dozen light-years across. At their very centres, the crush of gravity is almost unimaginable. It is here in these celestial cauldrons that theory has long predicted the missing link should be forged and found. If an EMBH truly lurked in the heart of a globular cluster, it would be utterly invisible to our telescopes. But its gravity, its immense and silent authority would be undeniable. It would act as a hidden dance partner, a gravitational gyroscope around which every other star in the core must move. Proving its existence required a feat of observational tenacity almost beyond belief. It demanded tracking the precise three-dimensional motions of individual stars in the cluster's impossibly crowded core, a task akin to tracking a single firefly in a distant fireworks display. using the world's most powerful telescopes equipped with sophisticated adaptive optics to cancel out the blurring effects of our atmosphere. Astronomers spent years, and in some cases decades, patiently mapping this stellar ballet. They measured the subtle shifts in starlight calculating velocities with extraordinary precision. Slowly, painstakingly, a picture of the invisible began to emerge. They found that the stars closest to the very centre of clusters like Omega Centauri or 47 Tucani were moving at incredible speeds, far faster than could be explained by the gravity of the visible stars alone. Their orbits were not chaotic as one might expect from a simple swarm. Instead, they were choreographed, whipped into a frenzy by a single massive and compact object hiding in the dark. By adding up the velocities of these frantic stars by calculating the gravitational force required to keep them from flying out of the cluster entirely, astronomers could effectively weigh the ghost at the centre of the dance. The results were breathtaking. Time and again, in cluster after cluster, the calculations pointed to a central dark mass of thousands, sometimes tens of thousands of solar masses, all concentrated within a space far too small to be anything other than a black hole. This was evidence of a completely different nature. It was not the sudden violent conformation of a merger, nor the brilliant flare of an accretion disk. It was the quiet, persistent, unyielding testimony of gravity itself, written in the orbits of 1,000 suns over 1,000,000 years. It was the universe's own ledger, meticulously kept showing a clear gravitational debt that could only be paid by the presence of an IMBH. This was the final piece of the puzzle, the keystone that locked the entire structure of our argument into place. The convergence was now complete and utterly compelling. Imagine the scene, a cosmic courtroom where the case for the missing link is finally being presented. The prosecution lays out 3 separate, unimpeachable lines of evidence. First, the gravitational wave detectors, which present recordings of their mergers, the audible proof of their existence and mass captured directly from the vibrations of reality. Second, the X-ray telescopes, which offer photographic evidence of them feeding their accretion disks shining like cosmic fingerprints. Their light signatures a confession of their immense gravity. And third, the meticulous stellar cartographers, who present their star charts demonstrating the orbits of countless stars that dance to the tune of an invisible massive object, a dynamical proof that is as certain as the law of gravity itself. Any one of these pieces of evidence would have been revolutionary. Together they are undeniable. We can now point to a specific globular cluster and say, with a confidence born from this triangulation of data, that the stars at its core are moving too fast because they are orbiting an intermediate mass black hole of approximately 10,000 solar masses. We know this because our models of stellar dynamics demand it. We can then turn our X-ray telescopes to that very same point and see the characteristic glow of a feeding monster, a flicker of high-energy light consistent with an object of precisely that mass. And while we watch, we can hear the background hum of the gravitational wave observatories, which confirm that objects of this exact mass category are not only possible, but are actively forming and merging throughout the cosmos. This is no longer a matter of speculation. The ghost story has been proven true. The creature from the cosmic shadows has stepped into the light. The missing link is missing no more. It is a confirmed, catalogued and growing population of celestial objects as real and as fundamental to the universe as the stars themselves. We have found it. We have weighed it. We have seen its influence and heard its voice. The search that defined generations of astronomy is in a profound sense over. But in solving this great mystery, we have thrown open the door to an even larger and more consequential question. Now that we know for certain that these cosmic bridges exist, what do they build? Now that the link is found, we must finally ask, what precisely does it connect? And so our journey through the cosmic twilight zone comes to a close. We began this exploration not with a triumphant discovery, but with a profound and unsettling silence in the data. We were faced with a cosmic ghost story, a tale of 2 vastly different families of black holes with seemingly no connection between them. On one side, the stellar mass phantoms, the collapsed hearts of individual colossal stars scattered like cosmic dust throughout the galaxies. On the other, the supermassive titans, the gravitational anchors of entire galactic empires weighing billions of suns. Between them lay a vast, inexplicable chasm, a demographic desert where a whole class of object, the intermediate mass black hole, was conspicuously absent. This absence was more than just a curiosity. It was a deep fracture in our understanding of cosmic evolution. It was a missing chapter in the epic story of how the universe builds its grandest structures. We had the beginning and the end of the tale, but the entire middle, the crucial transformative act, was missing. How did the universe leap from the mass of a single star to the mass of a billion? The question echoed through observatories and supercomputer simulations for decades, a persistent, frustrating whisper that hinted at a fundamental flaw in our cosmic narrative. Scientists were cartographers trying to map a new continent, but with a giant empty space at its very heart, a void on the map labelled simply, "Here be monsters," or maybe nothing at all. This quest was never about finding a single object. It was about finding a principle of nature, a mechanism for growth that could bridge the impossible gulf between the small and the sublime. We followed astronomers as they sifted through the glare of distant galaxies, searching for the telltale flicker of a star being violently torn apart. You witnessed how these tidal disruption events, these moments of celestial annihilation, could serve as fleeting lighthouses, their luminosity momentarily betraying the presence of a hidden mid-sized monster that was otherwise invisible. We descended into the glittering ancient cities of stars known as globular clusters, dense stellar hives, where the frantic gravitational dance of a million suns offered another path to the truth. There, by patiently tracking the anomalous speeds of individual stars, by watching their orbits warp and twist in ways that defied explanation, we found the gravitational fingerprint of an unseen central mass too heavy to be a star cluster, too light to be a supermassive black hole. It was a ghost in the machine, its presence felt not by what it radiated, but by the chaos it sowed amongst its neighbours. We learned to look not just at the centres of galaxies, but for wanderers, rogue IMBHs kicked from their birthplaces by violent mergers now roaming the galactic halos. These off-centre X-ray beacons and gravitational anomalies were the breadcrumbs that led us time and again to the lair of the missing link. Then came the new era, the dawn of gravitational wave astronomy. We learned to stop looking at the universe and to start listening to it. The faint, almost imperceptible chirp detected by our terrestrial observatories, the gravitational echo of a collision that occurred a billion years ago, provided the most direct evidence of all. It was the sound of space-time itself ringing like a bell struck by the merger of two objects, whose combined mass fell squarely, undeniably into that once empty chasm. It was the universe whispering its secret directly to us, a confirmation written not in light, but in the very curvature of reality. Each of these clues taken in isolation was compelling but circumstantial. A flaring beacon could be an unusual supernova. The strange dance of stars could be a statistical fluke. But when you weave these disparate threads together, the tapestry they form is unmistakable. The X-ray flare from a shredded star, the warped orbits in a globular cluster, the wandering gravitational heart of a dwarf galaxy, and the climactic gravitational whisper of a distant merger, they all point to the same conclusion. The ghost has materialized. The void on our cosmic map is finally being filled. What was once a theoretical necessity, a desperate conjecture to make our models work, has become an observational reality. The missing link is missing no more, and with its discovery, the entire story of the cosmos is being rewritten. This isn't just about adding a new object to the celestial zoo. It is about fundamentally re-engineering our understanding of how galaxies live and die. We now see that intermediate mass black holes are not merely curiosities. They are the crucial seeds, the primordial kernels from which the supermassive giants grow. Our models of galaxy formation no longer need to invoke exotic, unproven physics to explain the sudden appearance of billion solar mass black holes in the early universe. Instead, we can now chart a plausible step-by-step path of cosmic construction. It begins in the dense hearts of the first star clusters, where IMBHs form from runaway stellar collisions, or the collapse of primordial gas clouds. These fledgling black holes, ravenous and mobile, then sink toward the centre of their nascent host galaxies, drawing other clusters and gas streams with them. Through a relentless process of hierarchical, merging a cosmic feeding frenzy lasting billions of years, these intermediates coalesce their masses, accumulating their power, growing until they become the gravitational super-predators we see today. They are the genetic ancestors of the Titans, and we are finally witnessing their fossil record. Their influence extends far beyond this role as galactic seeds. Within the dense confines of globular clusters, they are not just quiet residents, they are active and violent engines of stellar evolution. An IMBH acts as a gravitational gyroscope, stabilizing the cluster against evaporation while simultaneously acting as a cosmic slingshot. It can eject stars from the cluster, entirely sending them careening into the galactic halo as hypervelocity runaways. It can capture stars into tight doomed orbits, slowly siphoning their mass. It can even catalyze the formation of exotic binary systems, flinging stars together with gravitational precision. These ancient stellar cities, once thought to be serene and unchanging, are now revealed to be dynamic arenas shaped and sculpted by the unseen gravitational artist at their core. In dwarf galaxies, the picture is even more dramatic. The presence of an IMBH can dictate the fate of its host entirely. The energy blasted out from its accretion disk can heat up surrounding gas-quenching star formation and effectively sterilizing the galaxy, or its powerful jets can trigger shock waves that compress gas clouds, igniting brilliant bursts of new star birth. The IMBH is both a creator and a destroyer, a cosmic monarch whose whims determine the destiny of its diminutive galactic kingdom. Finding them is not just about understanding black holes, it's about understanding the very ecology of the universe on a galactic scale. Now we stand on the precipice of a new golden age of discovery, armed with revolutionary tools that will transform our faint glimpses of these objects into a high-definition feature film. The James Webb Space Telescope, with its unparalleled infrared vision, is already peering back through cosmic time past the veils of dust that obscured our view into the epoch of the first galaxies. Webb has the power to see the feeble light from the accretion disks of the very first IMBHs as they ignite, capturing the birth cries of these primordial monsters. It can dissect the light from the most distant dwarf galaxies, searching for the telltale signs of gas being ionized by a hidden IMBH, or analyzing the motion of their star clusters with a precision that was once the stuff of science fiction. Webb will not just find more IMBHs, it will find the first IMBHs, allowing us to witness the process of supermassive black hole seeding, as it happened just a few 100 million years after the Big Bang. It is our time machine, and its destination is the cosmic dawn, where these missing links were first forged. But perhaps the most profound revolution will come not from what we see, but from what we hear. We are building a new kind of observatory, one that doesn't use mirrors or lenses. The Laser Interferometer Space Antenna, or LISA, will be a gravitational wave detector of unprecedented scale, an equilateral triangle of spacecraft millions of kilometers on a side floating silently in solar orbit. Where our ground-based detectors like Leo and Virgo are tuned to hear the high-frequency chirp of stellar mass black hole collisions, LISA will be tuned to the deep, low-frequency bass notes of the cosmos. It will listen for the slow, inexorable gravitational hum of a star or a stellar mass black hole spiraling into an IMBH over months or even years. We will be able to track this cosmic death dance in real time, a gravitational requiem played on the fabric of space-time itself, providing pinpoint measurements of the IMBH's mass spin and location. LISA will hear the mergers of IMBHs with each other, the very process of hierarchical growth that builds the supermassive titans. It will detect the gravitational waves from these collisions from across the entire observable universe, creating a census not of dozens but of tens of thousands of these objects. It will provide the ultimate confirmation, a symphony of evidence that will wash away any lingering doubt. With LISA, the universe will become an orchestra, and we are finally learning how to listen to its most profound and powerful compositions. Complementing these space-based observatories, a new generation of behemoths is rising on Earth. The extremely large telescope and the 30-meter telescope with their gigantic segmented mirrors will be able to resolve the star clusters in nearby galaxies with such clarity that they can track the motions of individual suns. They will create detailed gravitational maps of cluster cores, revealing the presence of IMBHs with irrefutable dynamic evidence. They will perform a kind of celestial archaeology, uncovering these cosmic fossils in our own galactic neighborhood. In the radio spectrum, arrays like the next generation Very Large Array will probe the faint jets and outflows launched by accreting IMBHs, a form of cosmic exhaust that signals the presence of a powerful central engine. Each new instrument operating in its own unique way will contribute another crucial piece to the puzzle. It is a multi-messenger, multi-wavelength assault on one of cosmology's greatest remaining mysteries. The era of speculation is over. The era of precision measurement is about to begin. Our quest to find the universe's missing middle has in the end revealed a cosmos far more interconnected, far more dynamic, and far more elegant than we ever conceived. The stark divide between stellar and supermassive was an illusion, an artifact of our limited perspective. We now see a smooth continuum, a seamless river of cosmic growth that flows from the death of a single star to the heart of an entire galaxy. We have learned that the universe doesn't build its giants in a single leap. It builds them patiently, methodically, piece by piece over billions of years of violent, beautiful creation. The discovery of intermediate mass black holes is a testament to human curiosity, to our relentless refusal to accept a gap in our knowledge. It is a story of turning a frustrating absence of evidence into a powerful roadmap for discovery. We looked into the void between the worlds of the known, and there in the deepest shadows we found the key that unlocks the history of the universe itself. The story is not over. With our new eyes and ears, we are poised to read the next chapter, to uncover deeper truths about these enigmatic objects and their central role in the great cosmic drama. The silence has been broken and the universe at last is beginning to tell its whole story.